Hello, everyone. In this lecture, we're going to talk about queuing theory. So let's move. This is the outline. First, we're going to introduce the queuing system and some definitions. Then we're going to look at the burst dense queues with infinite and finite capacity. And then we will have the third lecture on the network model of queues. Okay. And in the end, we're going to have a look at a case study, how to develop queuing network models for capacity planning in a healthcare system. So queuing system, queues by the name is actually the waiting lines. It's unavoidable in modern life. So if you go to the grocery stores, banks, department stores, amusement parks, movie theaters, and computer processing and communication systems, they all involve queues, okay? So queues are not just for humans. So those are humans. So humans waiting. These are the computing tasks waiting for the CPU to process. This is a data packets waiting in the queue and to be transmitted in the communication system. Now, queues are definitely not just about humans. So in industrial engineering, we look at the production systems, modern manufacturing systems that maintain queues are called inventories of raw materials, partly finished goods, and finished goods throughout the manufacturing process. So supply chain management is actually just as a management of queues. So queuing models, we are often interested at like answering the following queuing questions. First, how many customers are there in the queue on average? And how long does a typical customer spend in the queue? How many customers are rejected or lost due to the capacity limitations? And how busy are the servers? So typically a queuing system is described as follows. So first there is the arrival process. We assume the customers arrive one at a time and that the successive inter-arrival times are IID, and it's described by the distribution of inter-arrival times. So the inter-arrival time can be exponentially distributed, as we discussed, like in the previous lectures, can be exponential, but it can also be like general random distribution or deterministic, or along with k phases. That means you have k events to happen, k arrivals, then you count a single event to happen. Okay, so this is along k. So k phase is counted as one arrival, and then you have inter-arrival distribution with along distribution. So this is the arrival process. And second is service times, okay? We assume that the service time of successive customers are IID. They are represented by the same letter as inter-arrival time. So number of servers typically denoted by S. All the servers are assumed to be identical, and it is assumed that any customer can be served by any server. Capacity, typically denoted by K, it includes the customers in service. If an arriving customer finds K customers in the system, okay, he or she is permanently lost. If the capacity is not mentioned, it's assumed to be infinite. Now let's have a look at the two examples. The first one is MM1. What does MM1 denote? So previously we have 4, right? So we only define the first 3. So MM1. M means memoryless. Customer arrivals, Poisson process, inter-arrival time, exponential, memoryless, IID. So this means M is arrival process, exponential, memoryless. And the service time is exponential and also a memoryless. And a single server, but we don't have the capacity, a queue capacity. If the capacity is not mentioned, it's assumed to be infinite. So we have infinite, okay, capacity. Now, the second example, MG210. what does this mean? This means first arrival is exponential, memoryless. G is the service time general distribution, IID. 2 means 2 servers. Queue capacity is 10. So those are notations used to describe the queue. Now let's have a look at the general Little's law in the queuing models. So before we talk about the Little's law, let's first define those terms. The first one is L. L is the average number of customers in the system. LQ is the average number of customers waiting in the queue. So those waiting in the queue does not necessarily to be served. Average number of customers in the system, including those in the queue and those being served. Okay. W, average amount of time a customer spends in the system. So a customer can spend time waiting in the queue being served, and WQ is average amount of time that a customer spends waiting in the queue. So this is only counting the waiting time in the queue, but this one actually including the waiting and serving. Now let's imagine that entering customers pay money to the system. So the cost identity is actually average rate the system earns, okay? And this is equals to lambda AT times average amount an entering customer pays. You see here, this is very interesting cost identity, because average rate the system earns, for example, average rate the system earns per unit time, okay? Then times T, this will become average amount of money the system earns by time T. So lambda A is A denotes the arrival, okay? Arrival process. Lambda A is average arrival rate of entering customers. So if we times lambda AT, this will become average number of customers entering by time T. So you have, this is a number of customers. Now each customer actually pays the average amount. So if you times average amount an entering customer pays by the number of customers, average number of customers by time T, this actually equals to average rate, average amount of money the system earns by time T, which is equal to the average rate the system earns per unit time times T. So NT is the number of customers customer arrivals by time T. So lambda A equals to the NT divided by T. Okay. Now, this Little's law is valid for almost all queuing models, no matter the arrival process, number of servers, queue disciplines. Okay. So the cost rules, let's look at the cost. If each customer pays $1 per unit time in the system, okay, the LT will be the average amount of time system earns by time T. And the lambda AT is the number of customer arriving, entering by time T, multiplied by average time a customer spends in the system. So LT equals to lambda ATW. So if each customer pays $1, so LT equals to lambda ATW. So T and T cancel. So Little's law is L equals to lambda AW. What is L? L is the average number of customers in the system. What is lambda? Average arrival rate. W is the average amount of time a customer spends in the system. So arrival rate, average amount of time spent in the system equals to the average number of customers in the system. So each customer pays $1 per unit time. Now this is why in the queue. So this is in the system. And similarly, we can derive LQ. LQ stands for the average number of customers waiting in the queue. WQ is the average amount of time a customer spends while waiting in the queue. So LQ equals to lambda AWQ. So suppose each customer pays $1 per unit time while in the service. Okay. So average number of customers in the service equals to lambda A expectation S. Expectation S is the average amount of time a customer spends in the service. You see here, we have 3 different versions of the Little's law, depending on we are looking at the system, the queue, or the service. But these 3 are three cost rules, they are derived from the cost identity. Okay, let's look at this cost identity closely, and suppose the customer pays money in different ways, and then we will be able to get Little's law in three different versions. Now, we just finished the Little's law, and we're going to look at how to use Little's law later. But at this moment, let's look at the limiting distributions. So limiting probability, this is what an outside observer would see. Okay, xt is the number of customers in the system at a time t. So Pn will be the limit t goes to infinity, xt equals to n. This is a long run proportion of time during which there are n customers in the system. This is outside observer C. And the second limiting probability is what arrival C. So let's use AN to denote. So Pn denotes the long run proportion of time during which there are n customers in the system. So this is in the system. Okay. AN is a proportion of customers that find n in the system when they arrive. Okay. And Dn is a proportion of customers that find n customers in the system when they depart. So this is very interesting because when a customer arrives, he could see n customer in the system. Okay. When the customer leave, he can go back and see how many people in the queue. Okay. Now in the system. Now let's have a look at an example, see how these three terms, limiting probability, different from each other. Suppose we have a queuing model. All customers service time equals to 1. You see, inter-arrival time is uniform distributed between 1 and 2. That means when one person enters the service, okay, he spent like 1 hour in the service and then he leaves exactly, okay, deterministic. But the inter-arrival time, the next customer comes, is actually more than 1 hour. So every arrival finds the system empty because every arrival when it comes, the time is actually more than 1. So it found system empty. Every departure, so when the customer finishes the service, he departs because he departs at 1 hour and the next customer hasn't come yet. So leave the system empty. So A0 is the proportion of customers find 0 customers, okay, find the system empty. This is actually 100%, okay? And departing patient leave the system empty is 100%. But if you look at the proportion, long-run proportion of time during which there are 0 customer in the system, this actually doesn't equal to 100%, okay? Because you have customers in the service, and then once it departs and there's nobody in the system, then you have 0, you find 0 customer in the system. Okay, so the long run proportion during which there are 0 customers is actually not 100%. So what if AN, DN, what happens to AN and DN? Every arrival find there are n customers. Every departure find n customers in the system. Okay. What's the proportion? This is 0. Okay, they actually equals to each other. So on average, arrivals and departures always see the same number of customers. That's AN equals to DN. However, they do not in general see time average, PN. Okay. In any system in which customers arrive and depart 1 at a time, the rate at which customers find n, the rate at which arrivals the arriving customers find n, and the rate at which the departing customers leaves n, these actually equal to each other. So let's see why this is the case. Because an arrival will see n when the number in the system goes from n to n plus 1, because he comes, right? He sees n, then he joins, becomes n plus 1. A departure leaves n when the number of systems goes from, because he's the n plus 1, then he leaves, he sees n, that means the system actually goes from n plus 1 to n. So between any two transitions from n to n plus 1, there must be one from n plus 1 to n. That means you have two transitions from n to n plus 1. So in between, there has to be a reduce from n plus 1 to n. Then you can increase again, right? So the rate of transitions from n to n plus 1 equals to the rate from n plus 1 to n. So this is the rate at which arrivals find n, and the rate at which departures leaves n, they equal to each other. So this is a proposition that an, arrival and departures always see the same number of customers, but they don't in general see time average. There is a special case, they will see the time average, that is PASTA. PASTA is the abbreviation for Poisson arrivals. Always see the time average. So if you have Poisson arrivals, Pn equals to An. Okay, a Poisson arrival arrives at time t. The conditional distribution of what it sees upon arrival is the same as the unconditional distribution of the system state at time t. So that's why the Poisson process from any time to t onward is independent of the system history up to time t. Hence, arrival would just see the system according to the limiting probabilities. So this is called PASTA, Poisson arrival see time average. So in the previous example, knowing an arrival occurred at time t tells there have been like no arrivals between t minus 1 to t, because you have deterministic, right, service time. So the arrivals don't see time averages. So that's why this P0, A0, they don't equal to each other. But if you have a Poisson arrivals, okay, Poisson arrivals always see the time average. This is mainly because of this conditional and distribution and unconditional distribution. It's the same because of memoriness probability. Memoriness property. Now let's have a look at the example. Suppose we have M, M1Q. So M means exponential arrival, memoryless, exponential service, memoryless. And you have one server, one capacity, okay? So that means XT, the state space is 0 to 1, capacity equals to 1. Arriving customers enter only if the system is idle. So if he sees 1, he leaves, okay? What a outsider sees is actually P0 equals to, this is actually mu over lambda plus mu, okay? P0 is mu over lambda plus mu. P1 is actually lambda over lambda plus mu. But what a departure, what an arrival sees. So the arrival sees is actually A0 equals to 1, A1 equals to 0. Arrival sees 0 is actually is 1, sees 1 equals to 0, because when it sees 1, it departs. Okay. So the departure sees 0 is 1, and the departure sees 1 because a departing customer sees there are 0 customer waiting, because he's seeing the system is not idle, so there's no customer entering. So 100% he will see 0, and the probability to see 1 is actually 0. When he leaves, he see there's 1 customer over there. He couldn't see 1 customer, so this is 1. So L is the expected number of customer in the system. So L equals to 0, P0 plus 1, P1. This is lambda over lambda plus mu. So W is the expected amount of time a customer spends in the system. So W equals to 1 over mu, because when it's 0, the customer spends service time 1 over mu. When there's 1, he spends 0 time. So it's 1 over lambda plus mu. So based on the Little's law, L equals to lambda W. So this is true. So now, up to now, we finished the introduction of queuing system, and we defined a few terms, and also we introduced the Little's law. Now, so this concludes this lecture. We are going to continue to discuss burst test queues in the next lecture.